तो उसका लैपटॉप कहाँ है? नहीं इसी पे लगा हुआ था।
this type of
ठीक है। सब आ रहा है इसमें। मैं जाके बाल
आदमी को लिंक भेजा कि नहीं?
मुझे नहीं पता, अंकुश ने भेजा, जिसको भी भेजा।
उसी ने तो यूं ही तो बेवकूफी चल। अच्छा भेजा क्या? तो रेंज अंदर वाले रूम के अंदर वाले दीवार पे चलो। ये नोट्स ले गए? हाँ। क्वेश्चन।
एक होना तो चाहिए।
चला दो। Oh, nice. It's over.
It's over.
चाहिए तो नहीं।
स्लाइड्स तो दिखेंगे नहीं। दे देना।
मैं introduction तो कैसे? So I would like to call on this stage.
So, thank you for coming here. So,
Ankush has been doing his PhD
since we don't know how long, since
my era.
Avantila, there is food, drinks, snacks, sweet, and some science.
Some what? Ankush?
Satya बोल रहा है looking nice. वही सब आवाज जाता है. शमीक.
हाँ.
चलो हो गया. हाँ.
ये सब रिकॉर्ड होगा।
हाँ.
मतलब लाइफ टाइम के लिए तो वैसे बोल के रखोगे।
हाँ.
What are these sauces?
We should write that it's vegetarian and.
So the green one is like and coriander.
Yeah.
This is tamarind.
Which one do you like?
शमीक, ओए, शमीक, सत्या बोल रहा है धीरे बात कर.
Yeah, you don't put it on.
Yeah.
Yeah, we got it.
So what's the description here? What's inside?
This one. This is actually flour coated in inside instead of this. These are different methods.
Stuffed potato.
What?
There is. We made it.
It's in a water. Oh yeah. You know my name. Get you all fancy. Get you all fancy.
Hello, lovely boy. Oh, what? Right this time. ठीक है. आईला दाखवून दे. हाँ, बघून जात असते.
I know.
Yeah.
Heaven. Eight. Soon to be like 2.5 hours.
No, it's not. No.
So how many slides this time?
No, it's okay.
I told him after 1 hour. Cool.
You know what?
After 1 hour, that one counts. Well, 1 hour, 10 minutes a shoe. 1 hour, 20 minutes a chair.
After the Lagudas in the
Easy, man. I remember Mission's fancy just midway through his fine with it. Yeah, take care. You did a good job.
Yeah, because that
Yeah.
PC will come to the live actually.
So, take it.
Wax me?
Supplement and
दिसतंय का आलं समोर अजून वेळ आहे. अजून 15-20 मिनिटं आहे. मग बंद होईल थोड्या वेळ, मग परत सुरू करू आम्ही. ठीक 10 मिनिटात कार्यक्रम लाईव्ह बंद होईल, मग आम्ही परत सुरू करू. हो 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 पण बघत नाही. ठीक आहे, ठीक आहे, मी ठेवतो.
उसकी तो बहुत खराब हालत हो गई।
ठीक आहे, ठीक आहे. हो आता मी आता कामात आहे. ठीक आहे, बघत राहा. हा चालूच ठेवायचं, सुरू होईल. ठीक.
Are you Skyping with someone?
Yeah, it's live streaming.
माझी को भेज देख रही है क्या? शमी माझी देख रही है क्या? दिख रहा है? शमी दिख रहा है उसे? चेक करने के लिए बोल रही हूँ.
Oh, you're the one. Yeah.
सब उधर बैठ गए. यहाँ कोई नहीं बैठ रहा.
खाना जा रहेगा वही तो. Hi everybody.
Yeah, you can present. I'm okay. I'll be happy to sit and listen.
नहीं ये बता ब्लॉकर लॉकर के बाद लेफ्ट साइड दो बिल्डिंग के बीच में ब्रिज हाँ सामने लॉकर से लेफ्ट लिया तो दो बिल्डिंग के बीच में ब्रिज बना है तो उसमें राइट वाले बिल्डिंग लॉकर के बैक साइड थर्ड फ्लोर 3 हाँ घर से लॉकर की तरफ आता है लॉकर क्रॉस करने के बाद लॉकर का वो निकलता है ना जो अंदर से triangle, उससे निकल के लेफ्ट लेना लेफ्ट लेके सीधा सीधा आएगा तो लेफ्ट राइट दो साइड पे बिल्डिंग के बीच में ब्रिज तो राइट साइड
वे तेजस से बात कर रहा है क्या? तेजस ने 2 बार कॉल किया। तेजस से बात कर रहे थे क्या? काम के लिए पूछ रही हूँ, सीरियसली पूछ रही हूँ। शमिक
हाय तेजस। नमस्कार नमस्कार। गाड़ी के लिए सब जगह से
वेलकम
नंतर कॉल करतो.
कैसा डील करना नेक्स्ट टाइम.
अंकुश तेजस से
बात नहीं कॉल करके बात.
हाँ अगर शमिक से बात हो
इंडिया नहीं करेंगे. I prefer at least coming as a class.
हाँ तो बार बार इधर से आपको उठा के फिर जाना पड़ेगा.
कहाँ जाना पड़ेगा
अंदर बाहर
कहाँ अंदर तो एक बार ही सीधा से सामान के बाद
इसको ना जब हम सब छोटी छोटी क्वेश्चन में रिकॉर्ड करना
वो लोग ही मना कर रहे, कमेटी मना कर रही है लेके जाना.
Yeah, you can start.
Again, sir. That's it. So the food has already been done. I think
It's not a group meeting.
well, this is the first slide and also the last slide. That's it. Thank you. Thank you, madam.
Thank you.
Please go ahead.
Attention नहीं करा.
You're a celebrity. Already.
Shall we can you
Sorry. वो नहीं आ रहा पिछला नहीं. तो स्कूल में जब वो तो फेस कर इतना काला क्यों है? Sorry. इधर रुक. हाँ इधर इधर. ये छोटे. क्या फेस पे लाइट मारेगा क्या? बाइक लाइट निकाल कर मुंह पे मार।
So cool.
You have a big audience.
I think it's the food that's attracted people.
You have food?
Yes, it's Indian.
Did you cook?
No.
Okay, so nobody's here.
You are here. He's responding pretty quickly.
Do you have any plans for cricket team?
Yes.
So who's in his cricket team?
That guy. Money. These two.
Is he a good player?
Okay, you are not playing this game.
Should we pass him or fail him? Do you need him next year?
No, that's why we need to get rid of him. He's your friend. Please pass him.
I don't think he's sure.
I'm fine at many sort of.
Yeah, I saw that.
डॉट मिला था जगह फुल हो गई थी
They're awake in the night. It's one.
Is it allowed?
खाली हुई निकाल
You should have had them stay.
It isn't allowed. I told them. You can see later.
हाय नवीन न्यू जॉइन अभिनव
मैं संयुक्ता
आपका कंप्लीट हो गया मेरा टेंशन
बाकी टेंशन नहीं इसके कारण यहाँ
When was the last time?
Today I got his email.
I don't know. Supervisor is late, so. Another?
There is snacks. They're sweet as well. Coffee. I saw the list of criteria that Manual does it.
Okay. We can go in first. We can see our name. These guys are. And every customer is more. I sent them twice a year because you're anyway supposed to talk on the phone. So. Who knows what you heard? She's probably writing for it. Like private stuff. Yeah, I'll contact her.
You need to fill out that.
I know.
Except I don't fill out. Complete, so you complete, I don't.
Oh. Alright. Oh, that's good. Oh.
No one is with.
Or when you.
Yeah. And one with the meeting our property. Yeah. Because
नहीं
बता दीजिए
that's
All right, please excuse us, the audience. We have to have some discussion for the events.
Slightly different ways.
Yeah.
मुझे that's it
all the best. All the best, Ankush.
Logo about this studio.
अंकुश के लिए मैसेज
उसके लिए ऐसे रेफरेंस के लिए
लाइव लाइव चल रहा है
कौन है सामने सामने कौन है
उसके पेरेंट्स उसकी फैमिली अभी मैंने मैनेजर से बात किया ना बोल रही थी हाँ ठीक है सबको दिखा रही
It's live streaming. So I think they're watching it. I think
Okay.
Okay, let's go. Since we are stuff.
I mean, if you want to go.
किसी को तो दिखाना है ना।
मुझे कितना टाइम लगता है? Footage. We are getting footage, free footage. Yeah. Food is good. Thank you, Ankush. Yes. Ankush, coffee रखना चाहिए तो coffee. Few minutes. Starting.
तेजस को दिखा।
ये क्या आप रिकॉर्डिंग कर रहे हो?
लाइव।
ओह लाइव है। अवंती है क्या?
मतलब जितने लोग उनको से लिंक भेजा सब होंगे।
देखो हम तो कुछ दिख ही नहीं रहे। हम लोग ऐसे टाइम।
इस साइड से टर्न करो ना। So it's family and everybody has sent a link.
So like we are here for Ankush events. Yeah, present sir. Present. Hi.
Slow and takes his time.
Doesn't justify itself.
I think work for you with OPT. Yeah.
उसमें ना स्टॉप ब्रॉडकास्ट का ही ऑप्शन है, पॉज का नहीं है, इसलिए मैंने पॉज किया।
Most of the companies they just say, you know, sponsor. Sorry. Okay, Ankush, please go ahead. Let's start. All right. Good afternoon. Thank you everybody for coming here. I'm glad to see so many people in familiar faces. So I hope that I'll be able to explain a little bit about material science and take you to the world of materials today. And so you'll learn something, hopefully, because there are many people from different departments here. So, all right, let's start. So my name is Ankush, and I'll be talking about what I've been doing since since last 5 years, working on fabrication and characterization of SMA, shape and alloys, max phase, bilays, and composites. So why are we studying this? Because if you look at materials for high temperature aerospace applications, they require those materials which can withstand high temperatures, which can damp mechanical vibrations, and as well as provide damage tolerance. So single material structures have been insufficient in doing that. So 6 years ago, a MURI project, which is collaboration of 6 different universities, was started, where a multi-layer functional hybrid composite was proposed, which can provide various multifunctionalities, such as thermal protection by ceramic layer, damage tolerance and mechanical damping in this region, and then a polymer matrix composite which can provide structural health monitoring. But our focus, or our group's focus, was on this metal ceramic composites area. And one of the major focus of this work is on vibration damping. So there are multiple ways, majorly two ways to do vibration damping. One is external, by using dampers, external dampers, isolators, such as hydraulic or friction, or you can have a material itself that is being used in those structures that can damp, that can provide high damping. So this is what we are looking at. We want to build a material that can be a structural material as well as provide material damping. So what are the advantages of having a material that can do both simultaneously? It can reduce the need for these dampers. They have a lot of weight, so we get weight savings. And the overall structure or the design is much simpler. So for this study, we are going to use a shaping alloy and a max phase, which I'll introduce in the next slide. What is that and why for our study? So a max phase is a ceramic material. It's a ternary carbide where M, it's an early transition metal, that's in red. Let's say titanium. A, for example, titanium silicon carbide. So A would be silicon from blue, and X can be carbon or nitrogen. It can be a titanium silicon carbide. And it has ceramic as well as metals-like properties. So it has high stiffness, but also has very high fracture toughness. So, and it also has good corrosion and oxidation resistance. If you see, it's been used in applications such as heating elements. But what we are interested in this study for max phases is the high mechanical damping. So what do you mean by damping? It is, if you look at a stress strain curve, uniaxial compression, single just compress it and load it. This stress and strain for alumina, regular ceramic, it's linear, comes back. For aluminum, linear comes back. But for a max phase, you get these loops. The area under the loop denotes the mechanical damping or energy dissipation. Bigger the loops, bigger the dissipation. So what we're going to do is combine this high damping max phase, which even we can go to 1 GPa stress under compression and come back and dissipate a lot of energy. It's a shape memory alloy, which is also a very good damping material. So if you look at the uniaxial stress strain curve of titanium silicon carbide fully dense with nickel titanium, binary, very commonly known and studied nickel titanium, you see that it has larger damping than titanium silicon carbide at the same stress value. So, and the reason for damping in SMAs is because we have hysteretic movement of twin boundaries and martensite interfaces. Another advantage of SMAs or shape memory alloys instead of regular metals, they have first of all higher damping, and then they provide this shape memory effect. Shape memory effect means you can take a shape memory alloy and deform it, and when you heat it up, it comes back to its original shape. So it remembers its shape. By combining that shape memory alloy with a ceramic, you can introduce some residual stresses which can further increase our mechanical damping property. Nickel tie, because it's a benchmark shape memory alloy, that's why we're using a nickel tie. So if you look at the strain versus temperature plot of a regular equiatomic nickel titanium, so here at 150 degrees C, you cool, it cools under regular coefficient of thermal expansion, like regular metals. But at a certain point, MS temperature, it suddenly starts transforming and goes into a martensite phase here. So we get huge transformation strains. It's order of 2 to 3% under 100 MPa stress. And when you heat them again back into again here, you have some irrecoverable strain. That means we have transformation strain and we have irrecoverable strain. And so basically what we are going is we are going an austenite phase at high temperature, cooling it down and going into a martensite phase, and then again coming back to austenite. In this cycle, we don't recover all the strain, we have some irrecoverable strain due to dislocation generation inside the shape memory alloy, nickel titanium. Why this is important? Because our composite has a nickel titanium, has a shape memory alloy, and we want to study this behavior of our composite. So both SMA max phase are non-linear hysteretic materials, and you have to combine these two to get higher damping SMA max phase composites. That's one of the aims of this study. So what is the challenge we have encountered in this study? So when we process them, what happens is they react a lot. So we have a lot of reaction. So it's highly reactive. So one way, before going into processing of max phases, I think it's important to understand what kind of reactions it happens under various temperatures. And also, because we have this interface, reactive interface forming between the composites, we will also study mechanical properties. So the aim of the reaction study is to find processing parameters for composites. So we have minimal reaction between them. So if we combine two ceramic and a metal and then heat them up, if everything gets consumed, there is nothing left. So what's the point of combining those two materials? So we want to keep the reaction between the two as less as possible. So we have to find those processing parameters for composites by studying reaction between these two metals, and we're going to do that using joining. bilayer join. Another thing is mechanical properties, because interfacial mechanical properties are going to influence the properties of the composite. So, for example, load transfer can affect stiffening and strengthening of the material. Or if you have a very weak interface, crack deflection along the interface can affect toughness. So, it's very important to study microstructure and properties of the interface. So, how we are going to do that? We are going to use a nickel titanium silicon carbide composite. This is a composite animation. We have red particle, it's one phase, in green is another matrix phase. So in between those two phases, we'll have reactive interfaces. So by doing joining of these two separately, just taking bulk of those, titanium silicon carbide nickel tie, and studying this reaction thickness over different temperatures and times, we will characterize this, so basically interface, then join them, look at the microstructure, and then look at the mechanical properties of the interface, and then look at the mechanical properties of the composite. So this joining will help us, or reaction will help us find processing parameters for the composite, to process them to characterization, and then finally, because we have a shape memory alloy, to thermomechanical characterization. So what are the research objectives? We want to study reactions between nickel titanium silicon carbide under high temperatures. Why? Because that will help us in processing of composites with minimal interfacing reaction. Then we have to look at mechanical properties of the interface, and then because they affect the properties of the composite, and then look at the thermomechanical behavior of composites and also achieve high damping, as high damping as possible. So before we study reaction, we want to join them. Now there are various, so we are joining using two bilayer materials. This is a unit cell of a max phase where M is in red, A is in blue, and X is in gray. So titanium would be red, silicon will be blue, and X will be carbon. So here, if you look at, so usually what happens is in this max phase, A element or the silicon element is weakly bonded between, as compared to other metals. And when you heat them up, it diffuses out easily compared to other metals. So you want to use this reaction or diffusing out of A element from the max phase so that it reacts with the nickel tie and get joined. So what we started with, the pressureless diffusion bonding. What does it mean? It means that we have two bilayers, a ceramic metal, titanium silicon carbide nickel titanium, and put a tantalum wire around it so it doesn't react with the metals and ceramic. Evacuated them in a quartz tube, put them under a furnace and heated them up. And what we saw is at 1100 and 1200 degrees C, we see a reaction around the order of 55 microns between this nickel tie, that's titanium silicon carbide, it's nickel tie, titanium silicon carbide. And we see a lot of reaction. So we wanted to reduce it. So can we join them at lower temperatures? Using this way, we found that we couldn't join them. Probably because there was not enough pressure, because it's just holding these two together. Not enough pressure to join. So we didn't find any bonding at this 1000 degrees C. So what we did was, we started with a pressure-assisted diffusion bonding, where we have a titanium silicon carbide nickel tie pressed under alumina plates and bolts, and then we put it under a vacuum environment and then beat them up. So we see successful joining between 800 to 1000 degrees C and for different times, 1 hour, 5 hour, 10 hours. So, but one critical thing is the interface thickness is an order of magnitude lower. Here it's 2 microns, 4 microns, 7 microns. But previously we had 40 to 50 microns. So what we think is happening is we are getting a liquid phase above 1000 degrees C, that's increasing the reaction layer. And this is also supported by a ternary phase diagram as well. And below 1000 degrees C, we are looking at solid state diffusion bonding. But so basically the conclusion of this study is we can process the composites under those conditions where we have very little reaction. So basically in this range, 800 to 1000 degrees. And I'll use this information when we go to processing of composites. So why don't we get bonding at 800 degrees C for 1 hour? Probably because if you look at the thickness layer is quarter of a micron. That's very thin. That means it's 250 nanometers. So probably we're reducing the time and reducing the temperature. Thickness is much smaller, and that interface can't hold the cooling stresses. When you basically heat them up to 1000 degrees C or 800 degrees C, cool them down. While cooling, we get stresses, thermal stresses, and that thermal stresses cannot be withstood by the interface here because it's probably too small, too little reaction. So we don't have bonding. So then we wanted to move to microstructural characterization, look at what reactions it's happening at the interface. So we did a line scan using elemental dispersive spectroscopy where you get quantitative point analysis from here to here. What you see is intensity versus distance plot. Look at the left, it's nickel tie here, titanium silicon carbide here, and in between is the interface. So we have red is nickel, we have nickel here, and there is no nickel. There is silicon here, but no silicon here. So, but in between the interface region, we have first increase of titanium content, decrease of nickel content. So basically, a phase that only has titanium and silicon, green and black. And here, a phase that has titanium, silicon, and nickel. So a better way to quantify this is to use electron backscatter diffraction, where we get very nice colorful pictures. Here is nickel tie, this titanium silicon carbide. Then we have Ki2 phase, NiPi phase, basically intermetallics that are forming in between this reaction layer. And we propose a reaction mechanism that says we are from titanium silicon carbide, as per the weak element in the max phase, silicon comes out and it reacts with the Ki2 and forms this intermetallic at those temperatures. This titanium carbide was first of all present before starting the joining. It already was there in the titanium silicon carbide, but it could also be forming because of the silicon diffusing from the interface. So okay, so we have this nice joining from different temperatures, from 1200 degrees C, we have characterization. But what about the mechanical properties? So we want to look at the mechanical characterization of the interface. So we did some malindentation where we get hardness and elastic modulus. And what we see is, we see,
Ankush,
yes.
These are the only possibilities. Can you go back and just keep thinking? Is this because of the specific processing you did at the time? Or you could have other intermetallics or other compounds in between?
So we looked at different temperatures and times, right? From 800 degrees.
But from chemistry, are there other combinations allowed?
I think it's possible. These are all metastable phases. Yes, it's possible. This is what we see at that time, at that temperature. So basically, if we have diffusion of silicon and nickel, right, it diffuses out. So at some point of time, there might be some metastable phases that might be forming. But when we are looking at only 1 hour, it's a snapshot. In between 1 hour and 5 hours, we might be forming some phases, but that we cannot capture right now because we are only doing 1 hour, 5 hours, and 10 hours. So we looked at the ternary phase diagram, and there are multiple phases that are possible. But this is what we observe in these snapshots of time.
If you didn't do, this is experimentally observed.
Yes.
What could you have predicted based on the phase diagrams, let's say, available to you?
Well, there are multiple possibilities. I mean,
We have phase diagram.
in the backup slides. I may have removed it. It's not there. So basically, there are multiple possibilities, but it's difficult to predict what exactly it was forming because it's all metastable phases. And yeah, it's difficult to predict. Thermodynamically, we can predict, oh, this might form, but there is kinetics as well. What might form and what actually forms are two different things. So, yeah.
Which is influenced by the purity of the phases other than temperature and time.
Yes, the contents in the initial. And plus, what is the amount of pressure at those locations where you are getting joining, that can affect the phases as well. Because reaction kinetics is affected by the stresses it's under.
And you see, this is where I'm going with my question. You get something that may not be the most desirable interface. If you put some requirements, I want to have the most the highest fracture toughness, so conductivity, some property.
Right.
Would you be able to bias to control what form?
Well, with this study, no, because what we do is we do multiple reaction times and temperature. We form multiple interfaces, but we mechanically characterize only one.
So then let me ask the final question. How do you select pressure, temperature, and time?
For this joining, the temperature is selected, so we did the whole range from 800 to 1200 degrees C. About 1200, about 1000, we get a lot of reaction. So you want to reduce the temperature, to reduce the reaction. So if you go further 800 below, we don't get joining. So that's why we keep in this 800 to 1000 degrees range. But to process composites, there are two factors. One is reaction. One is the densification of these powdered, consolidation of these powders. Higher the temperature, better is the consolidation. So we want to be as high as temperature as possible, but reaction also increases. So we have only limited range where we get good densification in that particular temperature and less reaction.
So then the next step is, like the person is asking, what if, as a third criteria, you want to specify what kind of phase you want to have at the interface?
Why did you select that processing condition? Why did you
Which one?
That one. In more details and the characters. 1000, what was that?
Yeah, this is 1010 hours.
Yeah, that's right. 1000
Yeah.
an hour.
Why did you select that one?
And the pressure, what?
So, I mean,
we made a composite at 950.
980.
980. This
For-
is 1000.
Yes.
15 minutes. So the conditions are completely different.
Right.
Why did you select this one?
So we characterize many interfaces. We characterize almost all interfaces if you look at here. So there is a commonality between all these interfaces. It's almost a 3-layer interface structure. We have a layer close to nickel titanium, that's Ti2Ni, but some grow and at the expense of others. Some reduce. So I mean, so we only have 3 phases interface in the interface. Only 3 phases that are possible, or there are more possible, but that's what we see. So one question is, why did we select only this? We didn't just select this. We studied did characteristics of all of them, and found that these 3 phases here, these 1, 2, and 3 form in all of them, but different amount of thicknesses. Question is, can we say, is this the better interface than that? No. At this point of time, we cannot comment on saying, oh, this we would prefer to have this interface instead of that interface. No. We can't
What
say
about
that.
thickness of that interface and composition compared to composite?
So when we process the composites or at 980 degrees C, the interface looks pretty similar to what we see here. So that's one of the reasons also that we study.
But probably you could say maybe nickel titanium silicon would be better for the interface. You could select a condition where you get nickel titanium, mostly nickel titanium silicon instead of nickel titanium 5 silicon 3.
Because silicon may be better energy absorbing lubricant type. I was thinking titanium, Ti2Ni is a passive material, so it doesn't undergo a phase transformation. So then, do you want to have it? Is there a way to minimize that layer? Actually, that's all I was thinking.
I see.
But the other point from Dr. Karawan, maybe the silicon phase is a desirable one. That's very relevant.
I mean, looking at the interface, we can't really say which one amongst all these 3 phases, which one would we prefer the best. We'll have to do, ideally, look at, so make composites or bilayer of all these layers, and then characterize all these separately, and look at the mechanical properties. Say, oh, 800 degrees C.
Actually, to follow up Dr. Nagul's question, let's say we ask you which layer is more desirable for mechanical properties of the composite. What would you do?
I couldn't comment as of now.
Okay, what would you do to comment?
So basically, you look 2 or 3, select 3 cases. One case where we have more of Ti-NiTi, one case where we have more of Ti5Si3, and one case where we have more of Ti2Ni, and study these 3 mechanical properties of these 3 interfaces using what we do, using fracture toughness test of bilayers, And
Why not some other, I don't know, nano indentation?
nano indentation will give us hardness and elastic modulus. So we can say, oh, it's stiff and it's hard. But I mean, from
what I would select is something softer maybe. It's likely that if you have softer material, you have tougher materials.
yeah, if it's softer, then it might crack at the interface. So we might not get good load transfer. So the cracking will occur at the interface instead of having in the titanium silicon carbide. So the toughening mechanism might be different in both cases. So yeah, we just select one condition and we mechanically characterize only one as of now. We don't do multiple. But that would ideally what I would do. Pick these three conditions and
So
study.
based on this test matrix or the different processing conditions, the higher the temperature, the more of the intermetallic you get, the NITI.
So let's pick this 10 hours, 800, 900,000, right? So here, well, it's pretty much, so here as you go from 900 to 1000, you get more of NITI SI, more silicon usage.
The gray is the SI.
Yeah, so this is NITI SI, this phase. This is TI to NI, and the dark region, this which is bigger here, smaller here, is TI5 SI3. So we get more of NITI SI here.
So time and temperature influence favors the SI compound.
Yes, NITI SI. Maybe it's more thermodynamically stable at higher temperature and higher time. Maybe we are going more towards equilibrium when we go higher and higher time and higher.
So maybe it's few paragraph on this for future learning.
Okay.
How would you select the best interface, mechanical characterization, and then what condition would you use
Okay.
to have that? Which is a very good suggestion.
Right. So what would you process to get better mechanical properties of the
Right.
interface? Right.
Because you have maybe you have a choice.
Right.
One, you have more nickel titanium silicon. In another, you can have more titanium 5 silicon 3. Some other conditions you have more titanium to nickel. Which one might be better?
Better.
Yeah.
Right. Nice. Okay. So for mechanical property characterization, we picked only one, right? And so we get hardness and modulus of this only TI and SI phase, which is higher than both the nickel titanium silicon carbide. And modulus is also high. It's close, it's comparable to the titanium silicon carbide modulus, which is 263 and 278. So it's the NITI SI phase, we can say at this temperature and time is stiffer and it's pretty stiff and hardness is high. So, but this is hardness and stiffness. So you want to look at some qualitative, if there is a crack, how would the crack propagate? So we did some Vickers hardness. This was only for qualitative characterization. So we have this indent here, and the crack starts. This is the interface here. It starts along the interface between the NITI SI phase and titanium silicon carbide here, and then we have this primary crack, and we have also beta picture is here. We have this tortuous crack propagation. That means if the interface was weak, it should have propagated straight. We should have not have got this wavy nature. That suggests that probably we have some resistance to crack propagation in our the interface we are making at these temperatures and times. Another image, you indent, we have it cracking in the max phase, probably because of titanium carbide. Usually we don't see cracking in the titanium silicon carbide when we do indent. And it continues and stops near the interface, closer to nickel titanium. So what does this show? That okay, we have an interface at this temperature that is unlike brittle materials, brittle interface, and we have some resistance to crack propagation. But this is all qualitative. We want to move to quantitative.
Now go back to your micrographs. Okay, so your interface, your crack starts between mostly interface and the max phase, right? Reaction layer and max phase.
Yes.
So why do you think it's happening?
That's probably the weakest.
Answer Dr. Laguda's question. You can speculate based on your micrographs. Those TBSD results.
Okay. I see.
For example, show the, what do you have between?
Here,
Yeah,
so we
what's
have a
yellow?
titanium carbide that's forming. So maybe the interface between titanium carbide and the titanium silicon carbide is the weakest point, and that's where we have the interface.
Brittle,
But
very brittle.
very good. So if we could eliminate the NID-SI phase, let's say for assumption purposes, then we might or might not have cracking here. I mean, we can't say a priori, right? That okay, if we don't have this phase, would the cracking still happen here or not? We would not know.
Go back to the results, the indentation.
This one?
Next.
Next?
With a microcrack, with a crack.
With the cracks.
The cracks. So, yeah.
So where is the indentation exactly for
So
that?
the indentation is here.
That box?
Yeah, that box. And we have the cracking that starts here. So this is well interface and the titanium silicon carbide. So this is the interface here. And it propagates all along.
That layer, I mean, that the strip is the SI layer.
Yeah, NITI-SI layer, very close to the titanium silicon carbide. Yeah, this one. This one. Or, yeah, this one. This is NITI-SI layer.
And the conclusion is?
So here the conclusion is that we have, instead of having a stiff and hard interface or an NITI-SI phase, we don't have, we have wavy crack propagation. So qualitative conclusion, not quantitative conclusion here. So we want to move to a qualitative understanding of the fracture of the interface. From next, that's what the next plan is. I mean, we did already. I'll show you the next slides. So let me go back and say, okay, we first joined with the pressureless diffusion bonding, where we couldn't join below 1000 degrees C because it was a solid state. We had liquid state at 1100, 1200, so probably it's easier to join. When we moved to pressureless diffusion bonding, we could join in all temperature range, but this is only you could make small samples. So we got a spark plug sintering machine where we would be processing composites. So by processing large samples for fracture toughness test of the bilayer and composites as well, we want to use this to make bigger samples. So you can do some fracture toughness testing. So this is one of the tests that is being used for mixed mode fracture toughness of the interface. This is one layer. This is another layer, 1 and 2. Let's say this is titanium silicon carbide, nickel titanium. We have a notch, and there is pre-crack. And then this bilayer is loaded in a 4-point bending configuration. Basically 1 and 2 below, and 3 and 4. So basically it's loading, and we want the crack to propagate in this direction along the interface. That's our aim. So why we chose this test? Because the moment in this region is constant. So we don't have to worry about this crack length. When we make samples, the crack length can be this much or this much. We still should expect one critical load drop and one critical strain and release rate. And that's our interface GC. So that's why. So basically, if you look at the analytical equations by Evans, they predict a steady state energy release rate depends on M. Rest everything is material parameters. It's all geometry and material parameters. M depends on load. So basically, from experiments, we just want one load where crack starts propagating, and that will give us the constant or steady state critical state energy release rate. That's what we expect. So, but we had some issues.
Is it steady state, Ankush? Is it steady state?
Yes, in between the inner loading points. Because the moment is constant in this region.
Because of that, or because it is steady state? In other words, sometimes to keep it steady state, you may have to lower the bending moment. But based on your observations, can you observe that it is steady state?
No, we didn't observe it to be steady state. This is what the analytical model predicts, that it should be steady state. If the interface is same, identical, homogeneous all across, and you have one moment where the crack propagates, or one load drop, you see load drop, but the load should be the same where this crack should propagate till here. That's what this equation and the analytical equation by Evans predicts. But we don't observe it.
Yeah, because usually there's a transition period. You have the initiation, you have a transition, and then you go into the steady state if you have enough self-similarity, like enough length for the crack to propagate, and you keep everything constant. The applied load, the self-propagating geometry, which means probably you have enough length for crack propagation. That's all I'm asking. Do you have enough to initiate and then reach a steady state before you start going closer to the points of contact, or you apply the bending moment? Is it easy for you to resolve that observation, or is it happening too fast?
So when we tested it, we didn't find it to be steady state, probably because of the same reason that the interface, this length is too small as compared to this length. So we probably had initiation. But this is what the model analytical solution predicts, that if you have a shorter crack length as compared to this length, then you should get a steady state once you have the initiation already.
Is this what you're doing with John Whitcomb, that calculation?
Yes.
Because he can do both. He can check initiation and propagation.
Well, we had some other issues. I'll talk about this. So basically, we want to make the aim before we want to join these and then make a pre-crack. Now, we had some issues while making a pre-crack. So let's say we doing diffusion bonding under stress, we hit a notch before joining and we get a pre-crack. What happens is when you join them under these temperatures, we get cracking at these points. And so we thought maybe it's better to join them first and make a notch after. But what happens is because the exact location of interface is unknown, then we can go below or we can go above. So the better way, what we thought is to have a notch before joining, but use the stress. So let's say if you don't have stress in this region while applying, so basically make a die that doesn't apply stress here, so we don't have or have less stress, then we might have weak bonding here. And that's what we see, that when you join using that geometry, we don't see, we see a notch and a pre-crack that is formed between these two materials. And that's what we wanted to. So now we have joined, we have a pre-crack. Now you have to test it. So this is one video of, I'll just show the testing video. Basically, we go loops. Ideally, you wanted it to propagate. So what is this? We are loading in the 4.10 best tension. This is the titanium silicon carbide. That's nickel tie. This is the scale we are using. This is the inner loading points, and outer loading points are somewhere further away out of the image. And this is we do so that we can track optically the crack length. So what we expected is this. You have load, you have displacement. You get one load drop and you can get one GC value. But what we observe is this. We get multiple load drops at multiple load values. And that too, the loads keep increasing. The question is why do we have this behavior? It means the crack propagates at different loads by different amounts. It's a start-stop crack propagation. So there could be multiple possibilities. First is the interface GC varying at different locations of the interface? That's one question. Second is, why do we get this apparent increasing resistance curve behavior? Resistance curve behavior means you have to apply higher and higher stress to make the crack propagate along that bilayer interface. Third question, we see some irrecoverable deformation when we load and unload. Maybe nickel tie is deforming, but question is, does nickel tie start to yield prior to crack propagation or after crack propagation? That's the bigger question. When does it? So let's look at one question at a time. First question, why do we get this behavior? Is it probably interface is different? So when you look at microstructure of the crack propagation after, so this is after the crack propagation happened, we have this crack moving direction left this time. So we have this titanium silicon carbide, that's nickel tie, and we have crack in the titanium silicon carbide coming back along the weak NiTi-Si titanium silicon carbide boundary, going back again titanium silicon carbide and back. And this is pretty much the whole behavior what we see. So what we think is the resistance to crack propagation to the titanium silicon carbide and the interface is similar. That means if the interface was weak, very weak as compared to titanium silicon carbide, you should have got straight crack propagation along the interface. Should not have gone daily. That's one thing. What we also see is at different locations in the crack. We see a primary crack, we see secondary cracks. So this is the NiTi-Si layer, this is Ti2 Ni layer. Secondary crack stopping at nickel tie, that's expected because it's a ductile phase. So we have crack propagation along this NiTi-Si and titanium silicon carbide phase. But we also have crack propagation inside the actual interfacial layer, and this is Ti2Ni. So that's probably one reason why we're getting that behavior that crack is not just propagating along the interface, but also along the max phase or titanium silicon carbide. Next question is what we said. Why do we get the R curve behavior, the distance curve behavior? So we collaborated with Dr. Whitcomb's group. This is courtesy of Keith Ballard. He's doing the modeling part. Titanium silicon carbide, nickel tie. This is the crack, and at this crack, critical load drop. What we see is we calculate the volume fraction of nickel tie that has yielded, and as you increase the load, we see more and more of nickel tie that's yielded. That means nickel tie is yielding and consuming energy. That means that's why we get the resistance or increasing R curve behavior. Third thing, does nickel tie deform prior to crack propagation or not? So we looked at what is the load required for nickel tie to yield. That's around 110 newtons using a uniaxial stress strain curve of nickel tie. And then to avoid plasticity before crack propagation, we need PC to be lower. But after doing experiments, what we found is the critical load, after doing various experiments, all the critical loads were higher than this yield load. That means we have plasticity in nickel tie prior to crack propagation. So we cannot use this analytical model by Evans, where it just uses assumption is elastic behavior. But what we can do is we know at this load neither nickel tie has deformed or neither crack has propagated. So till this load, we can use this as critical load and get a lower bound of GC for the interface, which comes out to be 115. So that means interface GC is at least this much. It might be higher, but we don't have nickel tie deformation because it's lower, PY hasn't reached, and we don't have crack propagation as well. So that we think it's at least this much. Now, how does this value compare with the literature values? So if you look at, this is what we get, less than greater than 115. 26.6, it's an order of magnitude difference for most glass, steel epoxy, aluminum glass, different systems. So why can they measure the GC and why cannot we measure? Probably because in their studies, crack propagation happens before the metallic phase deforms. So the interface is too weak, or they neglect the calculation of at what stress the metallic phase deforms. That means there is an interplay between interfacial strength and the strength or the yield strength of the metallic phase or the lower yield strength phase in the bilayer structure. Whichever gives first, that will happen. So,
yeah. Do you have the individual phases like for nickel titanium or the silicon carbide?
We have under pure mode 1, titanium silicon carbide under pure mode 1 is 7 MPa meter half K1C.
So it's 7 to 16.
7 to 16. That would be around, I think, 120, 130 GC for max phase. It depends on the elastic modulus as well. So from GC to K, we have elastic modulus dependence.
So the same, this is GC. What would be GC for nickel titanium? Or for titanium, silicon carbide?
I don't know.
I think for the when you calculate for the silicon carbide is about 120.
Pure mode 1 though. It's pure mode 1. This is a mixed mode configuration where we have mode 1 as well as mode 2. 75 is the mode mixity here. So we have almost 70% mode 1 and 20-25% mode 2 and 5% mode 3.
And how much do you think that different? Like if you have to guess, mode 1, mode 2.
So for titanium silicon carbide, pure mode 1 is 130. So as you go from mode 1 to mode 2, it increases. It increases, but how much is, I don't know. But what we can say is...
So my question is the interface stronger than the phases or weaker than the phases?
I think there are two ways to look at it. One is that it's at least this much, so it's comparable to titanium silicon carbide in port 1. And the fact that crack propagates in the max phase, you can say it's comparable. We cannot surely say it's higher or better. The interface is better than the max phase or not. But it's at least, I can say it's comparable to the values of pure titanium silicon carbide. Nickel tar, probably not, because it has probably much higher GC value than the interface, because of the plastic deformation in the nickel tar. In martensite, austenite will have
what
transformation.
But it has a much lower modulus, so you have to take that.
Yeah.
It may be 200, 250.
Yeah, because
that's
of
what
the
I'm saying, because of the low modulus.
Yeah, there's not much plasticity, at least what it is.
Yeah, that's something you should add. Definitely. I mean, you can calculate this at a separate column for the nickel time for the
silicon carbide. Okay. Pure nickel tar, pure titanium silicon carbide.
No, the work which is done with Theobox evaluation, just nickel titanium fracture for initiation for steady state. That may be interesting to compare, but of course for your middle phase probably is more of the max phase.
This value was close to max phase, so we're very excited.
Yeah, and it's at least as good as, usually interfaces are very weak, and you have metal ceramic composite systems, interfaces are brittle and weak, but this is at least as good as a ceramic, which is a good thing, and the crack goes in the max phase is also another good signs that we have. So in summary, we have, this is the whole summary of the interface study, that we have joint bulk components, we have interfacial structure has been characterized, modulus is higher, hardness is higher. The interesting part is this: we have nickel tie deformation prior to crack propagation, as well as the lower bound is higher than most of the literature that we report. So we have a strong and tough interface. But how does this help in our interface study? The reason we started this interface study was so that we can get processing parameters for components. That's one. So we have to minimize reaction and preserve our constituents. Basically, you have to keep the temperature processing this much. But the lower you keep, the less densification you get in composites. So you want to get as much fully dense sample as possible. So you have to move this side and stay below 1000 degrees. Another interesting part is mechanical characterization. So let's say you have a crack in the composite. So if you have a weak interface, the crack would propagate along the interface. But we have a strong and tough interface, so we have a start-stop propagation. Good bonding means we have good load transfer. It means prior to crack propagation in the composite, you might have some plastic deformation of nickel tie, which is a good thing. You want to dissipate as much energy and make the GC, K1C edge higher as possible. So we move to composite study and want to process them first. So we use this spark plasma sintering. It's a rapid sintering technique, so we can have as less reaction as possible. What we do here is we take powders of titanium silicon carbide, powders of nickel tie, combine that as close as 1000 degrees as possible, because you don't want porosity in here. You want as less porosity as possible, but we keep the time as little as possible to avoid reaction. And so as at that time we could maximum stress we could apply 100 MPa. That's why we used to use 100 MPa stress. So basically process under 90 degrees C, 10 minutes and 100 MPa stress. And you want to look at how does the shape memory behavior occurs in the composite. So we did DSC and found that the transformation temperatures don't change. It's pretty much binary nickel tie. We get a thermomechanical characterization of the SMA max composites. This is very much similar behavior to a bulk SMA, pure bulk SMA, that we have higher and higher loops under higher stress, higher transformation, higher irrecoverable strains. And then we look at the transformation strain versus stress plots of nickel tie. It's in red, composite in blue. What we see is transformation strains are lower. That's expected because we have 50 volume % of nickel tie. But irrecoverable strain is same as nickel tie. That means if you do a ratio of irrecoverable to transformation strain, we might get higher in the composite. That means there is some irrecoverable deformation because of the titanium silicon carbide that's present. So there's bending or kinking that's happening in titanium silicon carbide. Next, how does the damping look? Because we're concerned about the energy dissipation in the composite. So if you look at a stress strain curve at 200 MPa stress, adhesion silicon curve is black, it's pretty less. Red is nickel titanium, it's higher than adhesion silicon carbide. AS means as sintered composite. So you make at this temperature, you process it. We get higher energy dissipation, area in the loop is higher as compared to nickel and adhesion silicon carbide. But when you do this thermomechanical cycling, means heating, cooling under stress for 8 to 9 cycles, we get much higher or increased energy dissipation. When you plot this energy dissipation as WD, that's millijoule per meter cube, at all stress values, the thermomechanical cycling is higher for all stresses. Then we have the composite, and then we have the nickel tie, and then we have the titanium silicon carbide. And this is because we get contributions to damping because of porosity. We have nickel titanium that's contributing, that's titanium silicon carbide, as well as some twins forming in the interface that gives us further high energy dissipation. Now, how does this energy dissipation compare with the literature or in the global scale? If you look at loss coefficient, that means energy dissipation WD divided the total energy you input. So we have polymers which are very high but very low modulus. This is modulus, loss coefficient, very high. As you move higher and higher modulus, your energy dissipation drops. Composites come in here. Our material systems are in here. So it's higher than most composites, but the modulus is still low. So one way to improve the modulus is because we have porosity. We can reduce the porosity and increase the modulus of this composite. Then to just summarize quickly this composites work, we have thermomechanical behavior similar to nickel tie, expected because we have same nickel tie access composites. Energy dissipation or mechanical damping is higher in thermomechanical cycle composites as compared to as sintered. It's still higher than nickel tie silicon carbide. So it's highest in composite. And then this is the contribution towards damping. But there is an issue. We still have 15% porosity, which gives us very low strength. So what we did was we processed the same sample, kept same processing conditions, increased the stress. Instead of 100 MPa, we went to 200 MPa. And we found high density versus low density transformation strain comparison under different stress. And I expected the blue is low density, LD means low density, 15% porosity, ID means 8% porosity, so less porosity. So from low density to high density, we have lower transformation strain because titanium silicon carbide is the ceramic phase and is carrying more stress. It's expected. And this behavior is also similar to what we have seen before. The high density composites, we have higher irreversible strain. But how does the damping compare for the high density composite? That's the interesting part. This is the old low density sample. It's higher than nickel tie. But if you look at the high density composite, as sintered, it becomes lower. And thermomechanical increases, but it's still lower. If you plot WD versus stress for all stresses, AS means as sintered, low density here, and this is thermomechanical. Thermomechanical definitely increases our damping, but high density reduces the damping. So what is the advantage of having a high density? It's the stress. Means when you do uniaxial stress test comparison, you get higher compressive, ultimate compressive stresses. That's for high density. Low density is somewhere here, 250 to 275 MPa. We have pretty much increased. Why is this variation? Because probably we are not getting, there is chunks of porosity in different regions of the composite. That could be contribution. Or the amount of nickel tie and max phase in that samples is probably different. So it's not 50-50. And that's a processing issue that might be happening. But we need to do more work on this part. Why are we getting such a large variation in this behavior? So basically, high porosity, you have high damping but low strength. Low porosity, low damping but high strength. So maybe we can increase the damping further. So in overall conclusions are we have an interplay between strength of interface and metallic alloy that governs fracture. We have a strong and tough interface. Composites, we have excellent energy dissipation, and there are some extra irrecoverable strains because of additional contribution from titanium silicon carbide. Future work, if we can reduce porosity, that can give us higher strength, higher damping at high stresses, higher elastic modulus, and even higher fracture toughness because you have less chunks of porosity, pores can further increase the fracture toughness. So our next goal is to see what is the fracture toughness of these composites. because you want to use that fracture toughness. Then how does this energy dissipation of composite in different phases, like austenite, which is supposed to have much higher dissipation. Then how can the thermomechanical cycling improve this damping and fracture toughness? And then look at the high temperature SMAs, which are hafnium, zirconium, which can even take high temperatures, further high temperatures, because nickel tire was a base material we started with. It's the first time we started this work. So, so that's what we would like to go in the future. And finally, I would like to acknowledge my collaborators for processing and characterization work, and funding agency, Air Force Office of Scientific Research. And thank you very much. If you have questions, please ask.
All right. So questions from audience. Thomas?
Yeah, Ankush, would you please look at your Ashby's graph? I think it was slide 32 or something. Yes, that line, the dashed line, that where all your samples fall above, is it like a specific application?
That's a good point. I don't know why that's line.
So you didn't put that on in the
No, it was
okay.
already there. We just used and added our
Okay, I see.
component. Do you know?
That line is that where the product is 0.04 GPa. So that's,
Oh, the eta versus
Yeah.
E.
Oh, all right.
I never paid attention. Thank you.
so that whenever we use it as some figure of merit. It's very rough.
From the committee? You have questions?
I was expecting more sections to be presented.
What hurdles do you see in actually applying this technology to a first application?
What problems?
Yeah.
So
In other words, this looks very interesting, right? So why don't we do this right now? And what would be that application?
So we can use for two things. One is fracture toughness, we haven't done, we need to do that. So if we can use it for high damping applications, where pure shape alloys are being used in as damping applications in buildings, constructions, where you can put them as dampeners below the structures of the building. So we are increasing the damping further of those material as compared to SMA. So that would be one area. But the cost would be an issue and the processing would be an issue. Second thing is in aerospace applications where you require good elastic modulus, high elastic modulus, high fracture toughness, that means structural capabilities as well as high damping. That would be one of the future applications, but not right now. We cannot do it right now.
Yeah, I wonder about robustness compared to other methods of damping. You want something that's going to last a long time. So can you say anything about lifetime or?
Well, we haven't done an effect of time, number of cycles on how does the damping change as the effect of cycles. Like so.
Probably did all right.
Is this an area?
You did some, we measure models.
We measure modulus.
Change to see if there is a damage accumulation. Like after first cycle and after a high performing cycle. 100.
Well, we did for nickel tire. We didn't do for composites.
We did for heavy. Okay.
You consider this a viable area of continued research?
Yes, I think so. I think the fracture toughness would be very interesting to see because we expect the fracture toughness to be higher as compared to the pure max phase, or at least as much with start and stop propagation because you have strong interface. So the propagation would not be catastrophic. It would be more of a.
Yeah. I think Dr. Hartwig is asking this higher level question. Okay, but you said fracture toughness would be higher, but so what? What would you do with it? Right?
Yeah.
I mean, where would you use it, or what is the So why should let's say somebody in the audience care about this material?
I see. So applications such as aerospace applications, which require high fracture toughness materials, where you have a crack or multiple cracks, and the crack doesn't propagate catastrophically. So you want to use a material like this where you can have high fracture toughness basically, and damping simultaneously. That would be applications.
I was somehow expecting the continuation of the story. You measure the toughness of the interface and something more about the phases themselves, like the NITI silicon. So then the interplay is what is important. Sometimes you want to have a weak interface.
Yes.
So you don't destroy the face, or you force the crack to go through that, depending on the loading or other conditions. So that is the story I was waiting for you to build. I have now measured the interface, and I know, let's say, the other interfaces, and then that's how we combine all of these. That's how we'll have the maximum fracture toughness for this composite. And that will go back to Dr. Hardwick's question. What do you do with that? Because you just have a property. And Dr. Carmel said, what do you do with that? So if you put it in the picture where you have phases, you have other interfaces also, because here you force the crack to go in that interface.
Right.
If you just bend the thick composite, where will it start? Where will it propagate? You have many other interfaces.
Yeah, we started work on the fracture toughness composite, but we couldn't successfully observe crack propagation. I mean, the test didn't work. So we tried that. We did try it for a couple of months, so, but it still didn't work. But we are still doing it right now.
So if you do, I mean, now the method you used didn't work very well. So if you would have another year, what would you try, or what method would you use to find out the fracture toughness?
I think
composite says that we can close the loop. So you measure the fracture toughness of the composite, and now you can, next step would be to change the interface and then do fracture toughness test again to see again. Going back to Dr. Lagos's question, we have 3 different interface layers. Which one is more advantageous for the composite mechanical response? So basically, you couldn't finish that work, but what technique would you use?
So I think that
to close this
loop. So the technique we are trying to use was double torsion. The reason probably it was not working because we are having very little samples. Maybe we can make bigger samples. We can still try that technique, double torsion, and try J1C method, which Jaylan is using. It's a compact tension test.
Okay.
Compact tension test. Do
people use compact tension specimens for measuring fracture toughness of interpenetrating composites? Or have you seen any work on that?
Interpenetrating, no. But
what do people use, or has anybody used?
Well,
there are, compact tension specimens, 4-point bending, and notched specimens, or double cantilever beam.
Because the compact we use for the other project, Dr. Kama, where you have one single phase.
So people use 4-point bending where they put a V notch, so single H V notch, or for composites, yes. It was most on carbon fiber reinforced composites.
Okay. I would like you to do this. I think early 90s there were a lot of work on metal matrix composites, right? So go back to those works. I haven't seen a lot of metal matrix composite work recently, or ceramic matrix composites. So go back to like those things and look at the methods. And I would like you to add one paragraph on like how you would close this loop. So what would be the best method? Would you continue with double torsion experiment, or would you choose something else? Not considering this, we had sample size issue, but assume that you don't have sample size issue. What technique would be the best?
Most of those were like either particulate or continuous fiber, so they used composite testing methodologies mostly.
For 4-point bending, you can make specimens.
4-point bending.
But what's the problem with the 4-point bending? Notch or 7 notch specimens?
You have to measure crack propagation. With double torsion, we don't have to measure crack lengths. right? You can,
Yeah, but
Ankush,
no, I mean,
I
there
think
is
since
another.
you're more on the material side, I mean, this is very useful, the analysis, the testing. But trying to close the loop, again, I'm going back to that. How, if the next student tries to choose the processing parameter,
right.
is the pressure going to be the same that you apply to make that interface? Or you have a different recommendation? If you can get based on the testing you have done, the analysis, the impact, even on just the fracture toughness, on how you process the material.
So I think we would continue to use the same processing conditions because we get good interface and strong interface, and then test the fracture toughness, close the loop for studying, and then change the processing parameters to have different thickness of the interface layer, and then test it that as well, and then compare. Oh, this interface gives me higher overall fracture toughness, so we can choose. But right now with this, we cannot say, oh, this is better or that is better. So we still need a parallel comparison with that.
From the nano integration, what other properties do you get?
We get hardness and we get elastic modulus.
And the modular.
Yeah, elastic modulus.
Did you put all of this together? As to see what happens, the fracture toughness, the modulus, the trends, in that space of the processing, again, I'm going back to the same.
So we tested for only one condition, the hardness, elastic moduli, and the fracture toughness.
Because you have a system, like if you have a different modulus, then the stress will be different. So then you may develop a different condition for that crack to complicate.
I see.
It may be worth, because you have done so much work, it may be worth having some conclusions that will help.
I see. Okay. Yeah, include.
And actually, another thing will come. We didn't have that capability before, but the new nano inventor, you could run different load levels, load, unload, and then you take acoustic emission to see when the crack forms. And
So you mean take each phase of the interface
Right,
and load it and see the load displacement,
unload,
load, unload.
yeah.
Okay.
then keep track of that.
And then predict from there, oh, this says this.
Yeah, when the crack forms in individual
Yes.
phases,
I see.
like the titanium silicon.
Okay.
All right. Questions? Then,
Actually, can you write this recommendation? This is very important.
yeah.
You have done the macro experiments.
Mhm.
How do you connect those now with the nano integration? I mean, suppose these are true properties that you measured and everything is fine.
Right.
Then now explain what happens with the nano integration, the crack initiation propagation. Can you explain that? That would be a great correlation you
Connection.
can make.
So hardness and stiffness. Do you prefer a high hardness, high stiffness interface, or do you prefer a lower hardness, low stiffness interface?
And also, after you make the measurements, with these measurements, can you explain the crack initiation and propagation you have seen on the nano indentation experiments?
One more thing. You need to put some. You need to put error bars on your experiments. So I use.
Okay.
You can put error bars by repeating the experiments or just same sample,
sample,
multiple measurements. So you are missing
Okay.
error bars in most of the floods. Okay. Other questions? All right. And audience, please excuse us. You want them? Or-
So say, hi to your parents,